Welcome. This video is going to look at more of the problems from Section 3 of Chapter 1 of the Brown SL Chemistry book. So number 61 says, list the main features of kinetic theory for ideal gases. So the assumption with ideal gases is that the gas particles are in constant motion. They collide with elastic collisions, which means no energy is lost. And they collide with each other and the container, which creates this idea of pressure. Kinetic energy or motion will increase with temperature. The space between gas particles is just ginormous, so the volume is mostly empty space, so the volume of individual particles is considered to be negligible or zero. And the same is true with intermolecular forces. Because of the huge space, the intermolecular forces have no effect on the neighboring gas particles. So part B says, explain the reason for the difference in behavior between real and ideal gases at low temperature. Well, at low temperature, real gases have less energy and less movement. That means there's less space between the particles. So now the volume and force do come into play. You can no longer ignore the fact that individual particles have volume and have forces attracting each other. Number 62 is somewhat similar to 61. It says NH3 forms a relatively strong type of intermolecular attraction known as a hydrogen bond, whereas methane does not. In fact, methane has that dispersion force. Because you might remember, NH3 is going to have that trigonal pyramidal shape with that lone pair up here crowding things together, whereas CH4 is going to be a nice tetrahedral shape. So NH3 is not only going to be a polar molecule, it's going to be a really polar molecule. And CH4 is going to be a totally nonpolar molecule. So how does that affect their behavior according to the ideal gas? Well, since intermolecular forces are going to be noticeable with NH4, NH4 is going to deviate quite a bit from the ideal gas, whereas CH4 should not deviate. And then number 63 is simply a multiple choice. It says gases deviate from ideal gas behavior because their particles, A, have negligible volume. No, that's part of why they behave ideally. Have forces of attraction between them. B, that's not true. We're assuming they don't have forces of attraction. So D is just the opposite. They're not attracted to each other. And C, polyatomic has nothing to do with it. So B and D are opposites, so one of those has to be false, and it's B. They have forces of attraction. That would be when they deviate from the ideal gas. So with question 64, we start getting into solutions. So just a reminder that IB tends to call molarity concentration, which is fine. But it's expressed the same way, moles per liter or moles per decimeter cubed. So if you want to think molarity instead of concentration, that's just fine. So question number 64 says, calculate the mass of potassium hydroxide required to prepare 250 centimeters cubed of a 0.2 molar solution. So I want to know how many grams of KOH I need, and I'm being told that I want 250 centimeters cubed, and it's going to be a concentration of 0.200 moles per decimeter cubed. So if I look at this, I know the concentration I want. I know the volume I want. So what I need to come up with is the moles required, and then I convert that to the grams of the KOH. So now before I can set this up, though, I need to convert either my centimeters cubed to decimeters cubed or vice versa. Centimeters cubed is probably easier to convert. It's just a simple process of dividing by 1,000 because there are 10 decimeters in a centimeter, but we've got it cubed. So this is really 0.250 decimeters cubed. So now I've got a concentration of 0.200 equal to N over 0.250. So if I solve for N, I'm going to get a molarity, moles of 0.0500 moles. And since this is KOH, then I can take the 0.0500 moles times the number of grams, the molar mass of KOH, which is 56.11 grams, times that 0.05. So we're looking at 2.81 grams of KOH to make this solution. So number 65, now we've got magnesium sulfate and it's hydrated. but I know the volume and the concentration I want. So you maybe noticed on the previous problem, or as the book indicates, N is really equal to C times V. So I've got C and V, so I can simply plug in 0.100 times 0.200, and I'm going to get 0.0200, and that's my moles. And now I have to come up with my mass for it. Need a 0 there. So let me pause while I punch this all in, because this could be a fairly massive compound. So I came up with 246.52 for my mass, and when I multiply that by 0.02, 4.93 grams is what would be required. So 67 is a pretty easy one as far as solutions go. 250 cc's of a solution, 5.85 grams of sodium chloride. They just want to know the concentration, and they want it in moles per decimeter cubed. So I divide by 1,000 to get my volume to 0.250 decimeters cubed. And I have to take my 5.85, so I've got my volume, take my 5.85 grams of NaCl, and I need to convert that to moles, and NaCl is fairly easy to find. You've got 23 for the Na, plus the 35.45 for the Cl, so 58.45 grams, which looks like this is going to put us right around a tenth. So 0.100, hanging on to sig figs, moles. So now I've got N and I've got V, and remember, I just have to divide those. 0.100 divided by the 0.250 is going to give me 0.400 moles per decimeter cubed. Number 68 is the first one where they're giving you a stronger solution or stock solution that you're going to dilute. So they want to know if you had 16 molar HNO3, what volume of that would you need to prepare 100 centimeters cubed of 0.5 molar decimeters cubed? And I actually don't have to change the 100 cc's because I could just express my final answer as centimeters cubed as well. So plugging in, C1 is 16.0. V1 is what I want to find. C2 I want to be 0.50, and V2 I want to be 100 centimeters cubed. And so if I solve for V1, I'm going to come up with a volume of, 3.1 centimeters cubed. Number 69 is looking at a titration, and we will do several of these. In fact, we'll do one shortly in class here. But you've got sulfuric acid and sodium hydroxide, so you need to balance the equation to see if they titrate or cancel each other out in a one-to-one fashion, and in this case they don't. And then you're being asked for the concentration of H2SO4. You know the volume, so you just need to find out how many moles of H2SO4 were in there. So I could take my NaOH, and I know I have 0.03642 decimeters cubed, since it was given to me in centimeters. I divide by 1,000. And if I multiply that by the 0.147 moles per decimeter cubed, then I find that I have 0.005353 moles, and this is my NaOH. So how many moles of H2SO4 do I have? Well, I have to look at my balanced equation here, and I see that I only have half as many H2SO4 because it's in a 1-to-2 ratio. So if I divide by 2, I only have 0.002677 moles of the H2SO4. So my concentration would be 0.002677 moles, and I'm going to change that to decimeters cubed because more commonly it's expressed as moles per decimeter cubed. And when I divide by the 0.015, my concentration appears to be 0.178 moles per decimeter cubed. So number 70, they're talking about gastric juice containing hydrochloric acid, 5 centimeter cube sample, and we'll write that down as our HCl, 11 centimeters of KOH with a strength of 0.01. So I've changed both of my volumes into decimeters cubed since we're using concentration here. So I could take my KOH, and if I have a 0.0100 moles per decimeter cubed strength, and I use 0.01100 decimeters cubed, then I know that the molar amount was 0.00011. You may want to use some scientific notation here, but that's my moles of KOH. Now in this case, KOH and HCl neutralize in a 1-to-1 fashion, so that's also my moles of HCl, and I know my volume is 0.00500 decimeters cubed. So if I divide that by the 0.005, I come up with a strength of 0.022, got an extra 2 going there, moles per decimeter cubed as my concentration of HCl in the gastric juice. For the second part of the question, they want to know if you assume that this gastric juice has a density of 1 gram per milliliter, just like water, and we've got 5 milliliters or cc's of it. We have 5 grams, and they want to know what's the percent by mass of HCl in there. Now, the book gives a different solution, and I don't agree with it because I think it's much simpler than what they make it. My solution hinges around the fact that we already know how much HCl we have, the molar amount of HCl. Our molar amount is, we said back here, I've got 0.00011 moles of HCl. So I should be able to just take this times the 36.46 grams per mole and come up with my grams of HCl present. And when I do that, I come up with 0.00401 grams of HCl, not moles. And so now if I want to set up percent by mass, I could take that 0.00410 grams, divide by the total of 5, and multiply by 100%. And when I do that, I come up with 0.08%. And it's very close to what the book comes up with. They carried a few more sig figs, but I think they did it in a much more complicated fashion if you look at the solutions manual with the book. So number 71, we've got this equation for sodium sulfate and lead nitrate. We know the volumes of each used, and we know how much lead sulfate was recovered. So the starting point is we really have to know how many moles of lead sulfate we have, because that will help us determine how many moles of each of the reactants we have. So 1.13 grams, if I take that times the molar mass, so 1 mole, 303.27, I guess I'm actually dividing by the molar mass here. So 1.13 divided by 303.27 lets me know I have 0.03726 moles of lead sulfate. So that allows me to work backwards here and see that 0.003726 moles of lead sulfate would mean I have just 1 mole of lead nitrate per mole of lead sulfate. I guess I don't need the parentheses there. So this is also my molar amount of lead nitrate. And then using the same reasoning, that would also be my molar amount of sodium sulfate. So now I could go ahead and calculate my concentrations of my 2 beginning solutions, because I have .003726 moles in 0.03530 decimeters cubed. Concentration of my sodium sulfate is going to be 0.106 is the concentration of, this is the Na2SO4, and then taking that same molar amount, 0.003726, and dividing by the volume of the lead nitrate, which was 0.03250 decimeter cubed, is going to give me a concentration of 0.115. So they want to know what assumptions were made. Well, the assumptions are that all of the reactants combined, that there was no leftover of either of the reactants, and also that all of the lead sulfate precipitated out and was able to be recovered and weighed, and also that there were no contaminants in there that set up any kind of competing or side reactions that may have influenced where some of these atoms ended up.